now we start the third problem of the tutorial 2. So, here we have to look for a Wiener filter design, and here is the form of the Wiener filter is given, that we have a signal, we need to remove the artifacts in the ECG signal ECG underscore HFN sampled at 1000 hertz. The equation of the Wiener filter is given here. It is expressed in the form of in the frequency domain, and it is expressed with the help of the PSD of the desired signal and the noise signal. Okay. So, first we need to be actually acquainted with them, that what would be the desired spectrum as well as the noise spectrum. We need to look at that to design the Wiener filter. Okay. So, Wiener filter is the optimal filter. So, it is a very important filter. So, let us move forward to see that. Now, we get some more description or some more instruction that how we can actually build that PhDs. For that, the suggestion is here that we can create a piecewise linear model of the desired version of the signal. Why that is told, that if we have the desired model of the signal in the time domain or the frequency domain, then I think that filtering is not required. If we already know that how the signal looks like without noise, then the problem is already solved. We would not take the pain to design the filter. As we do not have that, we are trying to approximate that with the help of piecewise linear model. The idea is, in that way we are able to remove or suppress the noise to a good extent, whereas we still keep the overall characteristics of the signal at hand. And we concatenate the piecewise linear model of different segments, P segment, QRS segment and T segment, and with that we can get actually the PSD of the approximate desired signal, and in between there are actually that places where the isothermal line is there the activities are completely noise. So, we can take those terms, that is the space between, especially between the T and the next P wave, that part we actually collect that, and that gives us the idea about the noise. Okay. So, we will select a few segments of the ECG signal and isothermal lines, that part we take the T to P segment, couple of these, and we get the noise PSD in that way by averaging these PSDs. Okay. And we select the noise segment, that is that which should be 0 mean, and then once we have the PSD of the signal and the noise, then we are ready to create the Wiener filter, and after that we need to compare the Wiener filter output with that of synchronous averaging and low pass filtering. Okay. So, that is the overall goal of this experiment. So, we start from the beginning. The first task is to collect the data. We get it from this link. We need to collect the MATLAB file to read that data, and we need to keep the input data and the MATLAB code in the same directory, that is the working directory of the MATLAB. So, once we are ready with that, we proceed. We get the Wiener filter. We need to first design that, So, the first thing that here the Wiener filter is a statistical approach. It is looking at the PSD of both the signal and the noise PSD, and we are trying to actually get a match between these two, where the signal strength is more compared to the noise, we would like to keep more input from there. Where the noise input is more, then we would like to suppress all such components, so that we can avoid the noise, and when both are in intermediate range, then we need to judiciously select that what should be the gain. So, how the Wiener filter does it? It minimizes the mean square error between the estimated random process and the desired process. So, desired process have a particular spectrum. So, what we try to do, that whatever the input signal is given, we try to find out a filter which minimizes the error between the desired process and the input process. Okay. And thereby we that whatever the output we get, we would like to reduce that, and that is the way Wiener filter works. Wiener filter, it requires the assumption that about the signal and the noise, that which should be weak sense stationary. It should be at least weak sense stationary, that means the characteristics should be stable, it should not change with time. So, for the non stationary signal, Wiener filter is not a good choice. Next thing, that we need to have the PSD of the desired signal as well as for the noise to design the Wiener filter. Okay. Without that information, that we are unable to design the Wiener filter. So, the first task becomes now to find out the PSD of the desired signal and the noise. So, we have to go for that. So, for that we proceed now, we try to first look at that signal, that how the signal looks like. We heard that this is corrupted with high frequency noise. So, we would like to plot the signal. For that, first we load that data, and we load the ECG data in the variable name called ECG, and we initialize the variable Fs with the sampling frequency 1000. L gives the number of samples in the vector ECG, or the number of data points available in the signal ECG using the command length, and then we create a time index. Instead of sample, we would like to plot it against the time to appreciate it better. So, we create a vector in the form of a ramp increasing from 1 to L, that is the sample numbers, and divide it by Fs, each of these sample, which will give us actually that the time instant of each of these sample. In fact, we can look at that we are multiplying it with 1 by Fs, which is the signal, that the time interval between two samples. Next is we create the pen for creating the new image using the command figure, and we plot the signal ECG with respect to the x axis, which is the time axis here t. So, here we are ready to see the signal, and signal we get here, it is highly corrupted with the noise. If you look at the QRS complex, because of high amplitude it is not clear, but we look it from this point to this point, that is T and the P wave, we get a huge amount of noise, that is very clear. Okay. So, we need to create the or design the Wiener filter to clean this actually signal. So, the first thing what we do, we take one cycle of it, okay, and first we have to create a desired actually signal, that is by the linear approximation of this. So, we plot this signal. Several times we have seen that how to plot one cycle. Here the only actually addition we can say that we have chosen only the first that 700 samples. Okay. Once that is done, we have done it by eye estimation, that we have the one cycle of the ECG. Next is we use a command G input after the plot. Okay. We plot the signal and we use the command G input, which will help that if we click on the signal, then all these actually from the left side we start and click these points, which can help us to build a linear model of the ECG signal. Okay. So, with that what we get, we are able to capture actually the x and y coordinate of these the points where we have clicked. Okay. So, let us see that how that looks like. The first thing that what we have done extra, we have shown that we have taken that the part of the signal from 1 to 700, that is only 700 first 700 samples we have taken, and we have assigned it to a variable called ECG underscore cell. Now, in this that we have the first cycle is cropped and that we have used for the display, and we also get because of use of the G input command that we have two vectors x and y, they are actually giving the coordinate of those points where we have actually clicked. So, we are getting the x in terms of that the sample instances, that is varying from 0 to 700, and more or less in between 0 to 50 we can represent with a straight line. Okay. 50 to 75 again with a straight line we can represent. In that way we are getting these that the abscissa that points. Same way we get the ordinates in the y axis. However, here one difference is there, that the magnitude what is shown here, that is normalized. So, we do not get actually this actually values to the scale. Now, to convert this the points, take it to the scale, what we need to do? We need to scale it with the help of the maximum value of that ECG signal within this segment. So, we are taking max into y, okay, max of this segment into y. So, that gives us the amplitude, and with that we are able to get that signal output properly. Now, what we do? We go next. We have to create a linear model or linear approximated model of the signal. So, first we have created a actually empty array, that 2/3 brackets that creates an empty array, and we have assigned the variable lin model in that way. The next point is that what we are doing, we are going through all these points that is collected, that length of x we are going from the beginning to the end or just last but one point, okay, length minus 1. And first check what we are doing, if the two consecutive values I plus 1 and I at these two locations, the ordinate value y, that is if that is same, that means at that point that should be a horizontal actually line should be drawn. Okay. So, for that what we have done, that we put the value a and we take the scale from the previous value y I and we multiply it with once I comma that range is x I plus 1 minus x I. Now, the reason that we use this command y, that once 1 comma this way, is that in between x I plus 1 to x I, in general there would be multiple samples. Okay. Here the 2 points we have clicked, number of samples are there in between. So, it should be a vector. So, that many samples we need to insert here to create a replica of the signal. So, we take it, we with the help of ones we create that vector of ones, and essentially that value what we get a, that is also a vector of constant magnitude with magnitude y I. Okay. Next point is, if these two are not equal, that y I and y I plus 1, then we come to this else portion. What we do here, we need to have a increase from y I to y I plus 1 in a linear way. And what should be the increment? The increment is given by that it should be the total deviation y for I plus 1 minus y I divided by the total duration in between. Okay. So, that is given by x I plus 1 minus x I. So, it gives the increment per sample, and with that rate we increase to create a ramp. Okay. So, with the help of that we put that ramp in the this variable a, and at the end we put one more sample because we are going not till the end. So, that part we take care, and at the end of it, once it is checked once, we append that with the that model, linear model, starting from that the actually a blank actually vector, it keeps on actually adding these A's and keeps on building in that way the different segments, and at the end of it, it would be ready when we come out of this for loop. So, at the end of the for loop, once our linear model is ready, the first thing is to look at what is the length of it, okay, that we get using the command length of linear model, and now we create a ramp from 1 to length of this linear model and multiply it with 1 by f s to create the time index for plotting this linear model. And for that we issue a command figure which creates a pen followed by the plot command against t1, the time index, we are plotting this linear model. Okay. So, that is the part we do, and let us see how this signal looks like. So, here we get the linearized model. Okay. So, we get the linearized model. Here the first part, that this portion it is giving the p wave, here to here we are getting the QRS complex, this is Q R S, and this part is giving us the T wave. Okay. And if you look at in between these portions, okay, So, these part actually we are taking as 0 or isothermal line, where actually we can expect the noise is there in the input signal. Okay. So, these actually signal is very important in that way. It not only gives us that a close approximation of the desired signal, but we also get where we expect only the noise deposition free from that signal component. So, next what we do, we create the PSD of that desired signal. As we have the signal here, that we know the signal, that lean model. Now, to create the PSD, the first point is to select that how many point FFT we would use, and as we are using FFT, it should be to the power of 2, to the power, say to the power n, in that form it will come. And if we take this value of n, this number to the power n, it should be large enough or bigger than that number of data points what we have. So, the minimum point what could be the value for actually this NFFT, the variable which will tell that how many points FFT we would take, it should be 256. And from the signal we would like to get that what should be the power, that what should be the length, which should be a power of 2, as well as it should be actually bigger than the linear model. So, for that first we take the length of it. We know the length of it is 700 in this case, in this particular example. So, here we use this command 2 to the power next power 2. So, this one next power 2 will give us the power actually that the number which is bigger than that 700, the least actually that the number which is just bigger than 700 is 1024. Okay. So, we get that value here, that 1024, and so next power. So, we get the corresponding value, that this part will give us the value 10, and 2 to the power 10 will get 1024 here. So, 1024 and 256, the maximum value is 1024. So, we take that in the next line for creating the periodogram. The first variable of the periodogram is the input signal. The second is for the window. Here we have chosen the default window, that is the rectangular window. Next we give that number of points for NFFT that we have chosen here, that should be 1024, and here the sampling frequency 1000 that is given. So, then we again create a pen with the new pen, creating created using the command figure, and then we plot it that against the frequency we take in the dB scale that power. Okay. So, that is why we take log to the base 10 and multiply with 10. So, now let us see how the plot looks like. So, here the plot is given in terms of the frequency axis, and other side it is in the dB per radian per sample it is given. What we get at the low frequency, the signal strength is high, and beyond a point it is very quickly diminishing. Even after 50, if we look at that, reduction is more than 40 dB. Okay. So, that is the nature of the signal. And next we look at how we can create the that noise energy. The noise energy already we have told that how we can get that. If we look at typical that ECG signal, so this is the segment where the isothermal line is the biggest. Here we can get it, then we can get it a little here. So, all these segments we can get, and we already know the periodogram is not a very good actually estimate, and because that noise what is white, that can give actually lot of fluctuations also in the PSD. So, we are going for that the average PSD for the noise. We are taking couple of segments for that. Okay. That couple of segments we are taking from multiple cycles, and at the end of it here what we have taken 3 such segments, and we have calculated that Px1, then Px2 and Px3, and we are taking the average of these 3, and the averaged one we plot it here in the new pen. Okay. And what we get, the frequency is more or less flat, much flat compared to that signal. Okay. So, that is the PSD of the noise. Now, we have to design the Wiener filter. So, for that what we have done, that first we create W, that the length of that Wiener filter in the frequency domain. We take that f samples of zeros first, and then we populate using that equation given there. But at the end of it we do not take the full length, because we know that beyond certain point the signal length is 0. Okay. It would be very low, and if we try to take something beyond first 200 values, experimentally we found this number, then the signal strength is very small, and as we are using this equation, then what will happen, as x is becoming very small, we get very large values, okay, and that part is not really useful. So, we take the IFFT of that, and as that filter should be a real one, we take the absolute value, because we are dealing with a real signal. Now, in this way when we are using FFT and IFFT, that we get the output from minus pi to pi. So, there is a phase shift, we need to make it actually 0 to 2 pi in that form we need to take. So, we need to use this command IFFT shift, and then we get the actually the filter output in the time domain. Now, once we have the filter, Wiener filter, we convolve it, that impulse response, with the input ECG signal, and we get the output here. And now, let us see that how the output looks like. Here we get that output looks very similar to the input ECG signal. It is that way pretty impressive that we got a good output. Now, the only thing that is remaining, that is we have to compare these signal with the 2 other cases. One is that Butterworth filter given here, okay, and next we will go for the synchronous averaging. Compared to the Butterworth filter, we see that though they are very similar, that there is some undulations there, which are actually shown in the P and the T wave. Okay. So, though this signal, that output has more we can say detail, there are some part of the noise is actually left behind in the output of the Wiener filter. Next, when we compare with the synchronous averaging, we see the output of the synchronous averaging is much more smooth. Out of all these cases, synchronous averaging is even better than the Butterworth filter, and then we get, compared to that, the Wiener filter has noise. So, that is the thing we observe. So, at the end we summarize the whole thing, we get first point that Wiener filter is able to suppress the noise, but not able to remove it completely. A little remnants is there, okay? And that is because that there is some overlap in the spectrum of the signal and the noise. Okay? We would not like to sacrifice that part of the signal. So, we are accepting a little part of the noise. Next is what we get, that output of the synchronous average, that is the smoother than the Wiener filter. In fact, it is the smoothest one, synchronous average 1. Output of the low pass filter, that using the Butterworth filter, is smooth, but slightly distorted compared to the Wiener filter. Okay. So, that is the conclusion we make for this third experiment of the tutorial 2. Thank you.